Where does that leave us? Well, here we are, we're back to Amy's. We have the real function up here. This is real life. There's a function which we don't know, which takes an input, lot area, and of course in real life, hundreds of other features, and it returns a price. Not forgetting that there's always going to be some kind of error term which we can't expect any model to pick up. Now we are going to estimate the real life function with our own model. Now let's imagine what happens if we estimate this using a simple model. The simple model might be a straight line. That's a straight line. From our polynomial regression, we would just have sale price equals some intercept plus a coefficient times the lot area. And presumably it would look something like that. On the other hand, if we tried estimating this with a complex model, it would overfit the data because there's noise in the data, and because it's complex, it can fit itself to that noise, and it would presumably look something like this. Where, as we saw before, in polynomial regression there were lots of squiggles because a complicated function can contort itself to fit the training data. Now imagine Amy's house pricing was an experiment, that the first 2,700 houses we have seen was experiment number 1, which generated the data set that we know as Amy's housing. But imagine somebody did this all over again and they generated a different data set looking at 2,700 different houses in Amy's. What would the simple model look like? Well, we know for sure it would be another straight line, and presumably it would have a slightly different slope because the new data would be slightly different. It might look like this, and if we did it again, there might be another one. The intercept might be slightly higher, but in general, it's going to be a line, and it's going to be upward sloping. What would the average of all those lines look like? Well, it would definitely be a straight line. The average of straight lines is a straight line. But what is interesting is that the average of all these models is the best straight line that would work for Amy's. Now, looking at this best straight line, is it any good? No, it isn't. Even the best straight line, even the average of all our models, just simply isn't complicated enough to fit the true relationship between lot area and price. Mathematically speaking, we can represent our average model as follows. It's the expected value over all possible data sets of all those different models that we fit. So it's a fitted model over each data set. And what we are saying with regards to simplistic models is that the average model is no good. How about if we go through the same kind of thought process with a complicated model? We've seen here what one complicated model looks like. You can imagine doing this again and getting a different squiggly line and again over different data sets generated from all the houses in Amy's. What would the average of all these squiggly lines look like? Can you guess? The average of all these squiggly lines would be exactly the right function. So, to recap where we've gotten to so far, if we have a simple model and we take the average of all simple models, then if real life is complicated, we are stuck. The average of simple models is always going to be too simple. On the other hand, if we try fitting really complicated models, the individual complicated models are going to be very, very wrong. But if you were able to repeat the experiment again and again and again, which, by the way, I don't believe you ever can do that. I've never come across a situation in my work where we can just simply have access to unlimited huge amounts of samples of data from the whole population. It doesn't exist. But if it did exist, and you took the average of all these complicated overfitted models, you would get the right model. So it turns out that we have 3 different sources of error when we're trying to predict the actual sale price with a function which we've estimated. The first one is a certain amount of error, which we are never going to be able to capture. Now, there's another source of error which we've been talking about, which is the fact that we're using a kind of model which is simply not complicated enough to ever capture the real-life relationship. The difference between the real-life function, which of course we don't know, and the average of all such simplistic models is bad. It's huge, because our simplistic models are just too simple. This source of error is called bias. The other kind of error we had was where the overall models might have been fine if we could take averages over hundreds of different data sets, but the individual models were very wiggly and totally fitted to the noise in individual data sets. This source of error is called variance. So we have three sources of prediction error: the bias, the variance, and the error term. Of course, if we add these all together, you will simply end up with what you would expect, which is that our error equals f of x plus e, which is real life, minus our fitted function. There you are. That's a little bit of insight from a mathematical perspective into what bias and variance are.